Hello everyone, welcome to the course Data Structures. This is Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. In this session, we are going to discuss about the AVL tree on deletion operations. Let us see the overview, what we are going to discuss under this session. As we have discussed in the previous session as what is AVL tree, introduction, and we have seen the insertion of AVL tree operations, and in this session we are going to discuss about the deletion part. Okay, and what is AVL tree and why we are going to use AVL trees, all these things we have discussed in the previous video. Once you can refer that video so that you can understand this deletion operation. Why? Because here also we are going to use some rotations to balance the tree. Here you can see AVL tree deletion. The first thing what you are going to do here is deleting of nodes from AVL tree is similar to that of insertion. When you are going to insert a node into the AVL tree, what are the conditions we are going to follow? Like we are going to perform some rotations like single rotations and double rotations to balance the tree. Here also we are going to follow the same procedure. But the main difference what you are going to see here between the AVL insertion and deletion, or see this one, imbalanced caused in the insertion can be corrected only with one rotation, either single rotation or double rotation. But here in insertion, if imbalance occurs, that we need to find out the first unbalanced node only from that newly inserted node by traversing towards the root node. By performing required rotation at that node, we will fix the whole AVL tree. That means from which node we need to rotate. After inserting a new node, from where we need to select that particular node, and from there where we need to perform the rotations. That will be done in the insertion part. But while coming to the deletion, this is little bit different when compared with the insertion. What is the step we are going to see here? But deletion of a node can imbalance multiple nodes in the tree. And this can be done as ancestry line up to the root node. That means from where you are going to have the imbalancing of the tree, from there to the root node, we are going to verify the balance factor. So, multiple rotations may be required to perform or to balance the AVL tree after deletion, right? We need to traverse all the way back up to the root node, looking for the imbalanced nodes and performing required rotations. While you are going to do the insertion, there we are going to perform only single or double rotations. And while doing the deletion, here you may require multiple rotations. This one you have to do. Multiple rotations to perform or to make the AVL tree balanced. Okay. Now, let us see what are the different cases that will occur in AVL tree deletion. As we have seen in the BST also the same cases. But in BST, we no need to balance any tree. Right. After deleting a particular node, we are going to replace that with either child node or its grandparent node. With these things, we are going to replace. But here in the AVL trees, these cases may be little bit different. What are the differences we are going to see here with the BST and AVL tree? Here, the same three cases here we are going to follow with AVL trees also. The node to be deleted is of leaf node. If suppose I am going to have a tree like this, right? If this is a tree, if I want to delete a leaf node, directly I am going to delete it, right? After deleting this node, I need to check the balance factor for each and every node on the tree, right? This is one case. And another one, the node to be deleted has exactly one children, right? Suppose if I am going to delete this one, suppose I am going to have a tree like this, right? Now, a node with one children I want to delete. In this case, what is the condition? I am going to delete this node, replace this one with this, and there you are going to stop with the BST. But here we need to check again the balance factor for every node, and if it is imbalanced, then again we need to perform the rotations, right? This is the second case. And what is the third case? The node to be deleted has two children. A node with two children, if I want to delete, suppose you consider this case only. If I want to delete this particular node with two children, it is having two children. In this case, what we are going to do? Either we are going to go for the left subtree, in that we are going to take the in-order predecessor. If I am going to select the right subtree, in that we are going to select the in-order successor, right? That one will be replaced with this, and then we are going to perform. If there is imbalancing of the tree after replacing with that, in that case, we are going to perform again the rotations, right? These are the things which we need to remember when we are going to delete an element in the AVL tree. Let us see. We are going to see all the three cases with example here, so that you could understand very easily what we are doing. Right? What is the first case? The node to be deleted is a leaf node. Leaf node means you don't have any children for that. Right? Now, deletion, the same thing. Deletion of even a single leaf from the AVL tree may imbalance multiple nodes at a time. Right? It may have some imbalancing of nodes in the tree. So, traverse all the way back up to the root node. Again, after removing any node, we are going to traverse back to the root node and find the balance factor from parent or deleted node to the leaf node in search of imbalanced node. To search the imbalancing of the node, we need to traverse from that particular leaf node to the root node, and we are going to find the balance factor for it and perform required rotations if found any imbalanced node. If there is imbalancing of a node, then we are going to perform the rotations. And you all know that the balance factor should be in between 1, 0 and -1. Only these values has to present for the balance factor. If more than that, or we're going to have a negative values, -2 or 2 or 3, anything, in that particular case, we need to perform the rotations. Let us consider the example here. This is a tree with all the elements. You can see 25, 22, 30, 23, 28, 40, 35 and 50. Now, I am checking for the first case. What is the first case here? I need to delete a leaf node. I can select any of these, but here I am selecting, I want to delete the element 23. Right? After deleting 23 means I am going to delete this particular node. Node is deleted. After deleting that, now check for the balance factor for each and every node. Right? Here, the balance factor for this is 0. Why? Because you don't have the left and right subtree. The balance factor for this is also 0. You don't have left and right subtree. And the balance factor for this is also 0. Why? Because this is 1. 1 minus 1 equal to 0. Right? And what is the balance factor for 28? It is also 0. And balance factor for 30, that is 1 minus, the left subtree is 1. 1 minus up to the leaf root node 2, that is the particular node to the leaf node, we need to verify the path, so that we are going to get the number of links in between those or 2, so that 1 minus 2 is nothing but -1. Up to now we don't have any problem, right? 22 we have 0. Why? Because you don't have left and right subtree. And for 25, here you have on left subtree you have 1. 1 minus from root node to the leaf node, we need to check either any of the path, right? 1, 2, 3, that is 3. So that we are going to get the balance factor as -2. Here, the tree is imbalanced because its balance factor should not be -2, right? So that we need to perform the rotation here. Which of the nodes to be selected to perform the rotation? Here on this particular root node, we got the imbalancing of the tree from root to from leaf to the root node. So that we are going to select this path. We are going to select the path from this one. When I am going to select that particular path, we need to perform. This is happening because of RR. That is RR imbalancing. We are going to have the tree to be imbalanced. So, we need to perform the left rotation. When I am going to perform the left rotation here, on 25, I need to perform the left rotation. When I am going to perform left rotation here, what happens? I am going to get 25 down, right? And 30 will be the root node and 40 will be the right of it. That means these 3 nodes we have selected. Those 3 nodes we need to select, and based on that we need to perform the rotations. Now for 25, you have left child is 22. We don't have any problem for this, for representing it. And while coming to the right subtree, for 30 you have the left child is 28. But for 30, the left child is already 25. But we don't have space to insert there. So that we need to check with 25, and that is 28. 28 should be inserted as the right child. Why? Because 28 is greater than 25, right? Because of that, we are going to insert 28 as a right child for 25, right? And the leftover 40 you don't have any problem. Directly we can insert 35 and 50, right? Like this way, we are going to perform the deletion of leaf node, right? This is one case. Now going for the second case, the node to be deleted has only one children. Again, here also, you may have a chance of doing multiple rotations when I am going to delete an element with one child. Okay. So, let us see the example here. This is a tree with all the elements which it was represented. Now, we are going to consider the case a node with one children. Here, 22 is the node with the one children. One children is 20. Now, I want to delete this node 22, right? When I am deleting the node 22, what happens? This node is going to be deleted. This is going to be replaced with the 20. The 22 is going to be deleted. For that, the child is 20. That will be replaced, right? Now, 20 is replaced. Now, what we are going to do? We are going to check the balance factor for each and every node. What is the balance factor here? For this is 0. For leaf nodes, no need to think of, it will be always 0. You don't have left and right subtrees. Because of that, 0. Now, for 28, what is the balance factor? You have the left child, but we don't have the right child. That means 1 minus 0 is nothing but 1. And this is also the left child. This is also 1. And when you are going to see this one, here for 30, you have the left subtree and right subtree. Both are there. Because of that, this will be 0. 2 nodes are there on the left subtree and 2 nodes are on the right subtree. That's why it is 0. Now, if I am going to see the root node, what happens to the root node? On left subtree, I have 1 minus. On right subtree, I am having 3 nodes to the leaf node from root. So that 1 minus 3 equal to minus 2. Okay, this is imbalanced, right? Now, again, we are going to perform the rotation. On 25, we need to perform the rotation. Which rotation we need to do? Because of this imbalancing, we are going to perform the rotation on the left side. That is, on 25, we are going to perform the rotation. Now, this is because of this side, right? Because of this one, we are going to rotate. Now, we are going to select these 3 nodes for performing the rotation. 3 nodes. What are the 3 nodes we have? 25, 30 and 40. These 3 has to be rotated onto the left hand side. Now, I am going to rotate it so that we are going to get, what are the 3 nodes we have? 25, 30 and 40. 25 and 40. These 3 nodes. You could observe 25, 30, 40. These are the 3 elements. The middle element is the median element. And the smallest element should be placed on the left hand side and the largest element must be placed on the right hand side, right? This is done. Now, what are the remaining elements that are present in the tree that has to be properly placed, right? After removing that, after performing rotation, now what we need to do? We need to have on 25, you have 30, right? This is done. After rotating up to here, on right of 20, left of 20, you have 20, right? Directly we can place it. But on left of 30, we have 28, right? So that where we need to place, as we have discussed in the previous one. On left of 25, you have already 20, but it is not, we are unable to place it there. So we need to place it on the right of it. Why? Because it has to satisfy the property of BST also, right? 28 has been placed. Next, 27, where we need to place 27? 27 is placed left of 28. That can be placed as it is. Why? Because you have the space for placing 27, right? Next, for 40, you have the leftover element 35. Yes, that can be placed as it is, right? Like this way, we can perform the deletion, right, for the single shade. Suppose if you want to do the same thing, suppose I want to delete the element 40. That in that also, you are going to have the same case. A node with one children, 35 is going to be replaced, right? That 40 is going to be deleted and 35 is going to be replaced with the 40. Now again check for the balance factor for each and every node. This is 0, this is 1, this is 0, and this is 1 minus 2 is minus 1. And here you have 3, 3 minus 1 is nothing but 2. Now again here it is imbalanced. This root is imbalanced because of this path, this one, right? So that we need to perform the rotation on 30. 30 has to be rotated. On which side we are need to rotate? Because of this path, it is unbalanced. Now we are going to perform left-right rotation. Left-right rotation. Don't be confused which of the elements has to come as a root node. Now, what are the elements we are taking here? 30, 25 and 28. Write them in the order, that is 25, 28 and 30, right? Now, according to this, this is the middle element. This is the 28 is the middle element. That should come as a root node among these three. So that what you are going to get, 28 becomes the root node. On left of it, you have the 25 and right of it, you have 30, right? Like this way you need to place, and the remaining elements we need to place it in the proper order. What elements we have left? For 25 you have the left child as 20, and for 25 the right child is 28. This is as it is, and this one is also 27. You don't have any problem with this, right? After representing the tree, you will be getting the final tree like this: 20 and 28. Sorry, already 28 we have removed, right? Now I need to get only 27. I need to get only 27. 28 is already moved to the top. That is as the root node. So that we are going to get 28, 25, 30 and 20, 27. And here for 30 you have the right child as 35. That one also we need to place. 35. 35 as the right child. Like this way the tree will be represented and it is balanced. And the third case, the node to be deleted with the two children. Here also, because of removing a node with two children, also imbalancing multiple nodes at a time. So to restore it, we need to use the AVLness property to get it violated by the deletion. Now check for the case 3. And here, this is a tree where a node with the two children I have selected, that is 68, is selected to be deleted. When I want to delete a node with the two children, here we have two cases. One is selecting, replacing that node with the in order predecessor. and other one is in order successor. Either with any of these we can replace, right? Now here with this example, I can say I am selecting the in order successor is replaced with 68. So you can see here 80 is replaced with 68 after deleting 68. Now in order successor is selected, that means the right subtree has been selected. We have only one node that is being replaced. After replacing it, now check for the balance factor. We are not checking with all these. Why? Because we are not work on the left subtree. Only we have worked only on the right subtree. Because of that, we are going to concentrate on this one first. If there is a balancing of that, we need to check the remaining part of the tree also. Okay. Now because of this is imbalanced. Why? Because here you have two nodes in the left subtree, and you don't have the right subtree, right? Because of that, this is imbalanced. Now what rotation we need to perform? This is happened because of LR. We need to perform left right rotation on these three nodes. What are the three nodes we have? We have 50, 55 and 80. As I said, 50, 55, 80, which is the middle element, that becomes the root node, and the left node becomes the left child and right node becomes the right child. Now according to that, rotate the nodes and place it as it is. Now 55 becomes the root node, 50 becomes the left child and 80 becomes the right child. Done. Next, coming to the next one, if I want to do the rotation, after doing that, check for the balance factor. Here the balance factor is not, the tree is not balanced because of some deletion we have done. Now you can check for the balance factor for each and every node. For 18, 0. For this one is, for 18, 0 I am writing. This is -1 and this 25 is 0, 35 is 0, this 0, 0. Why? Because all leaf nodes will be 0, and this is a -1, and this one could be 2 minus 1 is 1, and this will be 3 minus 2 is 1, and this is 1, 2, 3 and 4. 4 minus 1, 2. 4 minus 2 is nothing but 2. Right? Because of this one, it is imbalancing. So we need to perform the rotation. Which rotation we need to do? This is going to be rotated. 45 has to be rotated. On which side it has to rotate? It has to rotate on the right hand side. Because of this path, it is imbalanced, right? Because of this path. So we need to perform the right rotation. When I am going to rotate this one in the right rotation, what happens? 45 will go down, 28 will be the root node, right? 28 will be the root node. 20 becomes the left of it and 45 becomes the right of it, right? Now according to this, replace remaining elements can be placed. For 20 you have 15, 25, 18, place as it is. And for 45 you have for 50, 55, 50 and 80 as it is. And which are left over? For 45 you have, for 28 you have 30 and 35, right? For 28 you have 30 and 35, that has to be placed in the proper position. 28 right hand side you have 30, so that compare that with the 45, it is lesser than 45, so we need to place 30 here. And 35 is right of 35. Yes, we have placed for 35. So we are going to place like this. Not only performing the rotation, it has to satisfy the property of BST also. Right. This is how the third case is going to be. And let us check for all the three cases in the single example. Right. Here, let us take an example which covers all the three cases as we have discussed. This is the tree. First, we are going to delete 40. Deleting 40 element from the node, from the AVL tree. When I am going to delete 40, what is the first case? It is going to satisfy a node, deleting a node with a leaf node, right? Deleting a leaf node will be considered as the first case, right? This is the leaf node where we are going to delete. After deleting, check for the balance factor. Now check for the balance factor for each and every node here after deleting it. Here it will be 0, all leaf nodes will be 0, and this will be 1, and this will also be 1, and this will be 2 minus 2, 0, and this will be minus 1, and 1, 2, 3, 3 minus 1, 2, 3. 3 minus 3 is nothing but 0. After deleting, the tree is balanced. No need to do any rotations. Right? Now, sorry, here, this is deleted, right? Because of 40 is deleted, you have this is not minus 1. This is 2, minus 2. Because of this imbalancing of the tree, now we need to perform the rotation. What rotation we need to do? This is RL. Because of RL, this is imbalanced. So, we need to perform the RL rotation on this. First, perform R rotation, then perform on this right rotation. What are the three nodes we have? 50, 55 and 60. Now, 55 becomes the root node. 50 is the left of it and 60 is the right of it, right? Now, according to that, this is the tree where you are going to get 55, 50 and 60. Now, delete 60. Now, delete 60 from this tree. 60 is also the leaf node, right? The same case it is repeating. 60 is the leaf node. If I am going to delete 60, what happens? If I am going to delete 60 from here, what is the tree you are going to get? Deleting 60, what is the balance factor you are going to get after deleting this? This is 0, this is 1, this is 0, 0, this is 1, 1, this is 0, and this is 2 minus 3. This is nothing but minus 1. Here, no need of any balance factor, no need of any rotations. This is done. Now, I want to delete a node with one children. That is, I am going to delete 55. If I am going to delete 55, 55 is going to be replaced with 50. After replacing with 50, what is the balance factor for each and every node? Now you can see this is all leaf nodes will be always 0, right? And this is 1, 1, and this is of 0 because of 2 minus 2 is 0, and this is 1 minus 3 is nothing but minus 2, right? Because of this it is imbalanced because of this path or this path, any of this. Now you need to perform left rotation. We are going to perform left rotation on this. Because of RR, we are going to perform left rotation. Now rotate it. Each of the three nodes has to be selected 65, 70 and 80. 65, 70 and 80. In that, which is the median element? 65, 70, 80. 70 is the median element. So, 70 becomes the root node. 65 is the left of it and 80 is the right of it. Now for 65, the left element is 50, place as it is. But for 70, the left element is 68, but we don't have place for 68 here. So we need to place it as the right of 65. And for 68, left is 67, so we can place as it is. And for 70, right is 80 and left is 75, placing as it is. Okay, that is done. Now, after doing that, now I want to check one more case. Two cases we have done, and the third case is we are going to delete 70. That is a node with the two children we are going to delete. Right? This will be deleted. Now, after deleting that, either I can replace with the left, that is in order predecessor or in order successor. Anyone I can take it from the left subtree or right subtree. Now, but here I am going to select it from the right subtree. That is in order successor I am going to take. What is the in order successor here? I have 75 is the element that has to be replaced with 70, right? This has been replaced with 75. Now, after replacing, check for the balance factor, right? 0, this is 0, this is 1, This is 1 minus 2 is minus 1. And this is 3 minus 1 is nothing but 2. Right? This is imbalance. So we need to perform the rotation. LR rotation we need to do. LR. How we are going to rotate? What are the three elements we have? 65, 75 and 68. First represent them in the order. 65, 68 and 75. Now this 68 becomes the root node and 65 becomes the left and 75 is the right child. 68, 65, 75. Now replace the remaining. 65 left is 50 as it is. 68 left is 40. So we are unable to have 40 here. So we need to check with 65. 65 we need to check, but it is lesser than 65. Right? So we are going to place it as the right child. Right child of 65. But this is not correct. 68, 65 and 75. Okay. But here when I am going to place 40 as the left child of 68 is 40. But on left side we have 65. We are unable to place it. But 40 is smaller than 50. So that we need to place it here. Right? 40 is less than 50. So that we need to place as the left child. I can check the balance factor for this. 3. 3 minus 2 is nothing but 1. For this also 0, 1, 2. This will be not the one. 0, 1, 2. Right? Because of this it is imbalancing. So again we need to perform the rotation. After rotating, what you are going to get? Because of LL it is imbalanced. So we need to perform the rotation of it. What you are going to get? 68. You are going to get 50 as the root node and 40 as the left child. 65 as the right child. And here you have 75 and 80. Right? This is the final tree where you are going to get it. Okay. And let us see the summary what we have discussed in this AVL tree deletion operations. Under AVL tree deletion operations, we come across three cases mainly. One is deleting a node with no children, that is nothing but the leaf node to be deleted. And deleting a node with one children, we have discussed with example. And deleting a node with two children. These are the three cases as we have discussed. And you can try the example what we have discussed in this session. And you can take some more elements and try to perform the same deletion operations. I hope you understand this concept. Thank you.